So we have Bingqing Liu. She is an assistant professor at the University of Louisiana at Lafayette. She specializes in satellite oceanography. Her work focuses on coastal carbon dynamics, aquatic biodiversity, and water quality, and their responses to climatic and anthropogenic stressors. And then we also have Chusen Wu. He is an associate professor at the University of Tennessee, Knoxville, and an Amazon visiting academic. He specializes in geospatial data science and open source software, focusing on big geospatial data and cloud computing to study environmental changes. He created popular Python packages like GEE Map and Leaf Map. They are both Bingqing and Kushen. They are early adopters with the PACE program. And recently, Dr. Liu also is now on our PACE Science and Applications team, which is a competed position. We congratulate you on that. And with that, I will turn it over to you, Bingqing.
Thank you, Morgan, for the introduction. Just to do it real quick, can you hear me properly?
Yes.
Awesome. Hi, everyone. I'm Bingqing. As introduced, I will be talking about an open source tool called HyperCoast that we have recently developed for processing PACE OCI hyperspectral data. I will also introduce some of our research work that we have been doing to enhance HyperCoast capabilities in monitoring coastal water qualities using PACE OCI data, specifically focusing on phytoplankton, the primary producers in aquatic environment. Before my presentation, I would also like to acknowledge my collaborators. It is the collaborations making this work possible. One of my collaborators, Dr. Chusen Wu, is also sitting on this call for your questions later you may have. Next slide. Let's first look at the coastal ecosystem. They occupy only a small fraction of Earth's surface area, but host a variety of habitats, including coastal oceans, estuaries, tidal rivers, and diverse blue carbon habitats. Together, they serve as a very complex and dynamic biogeochemical reactor, making coastal waters extremely optical complex. Taking coastal Louisiana as an example, we have two large rivers, the Mississippi River and the Chapalaya River, which deliver tons of nutrients and sediments, causing eutrophication, harmful algal blooms, and hypoxia. So the famous dead zone in the northern Gulf of Mexico happening every year. We urgently need hyperspectral data to dive into more details about phytoplankton community structure. Next slide. Phytoplankton, the primary producers in aquatic ecosystem, it is an extremely diverse community with different cell morphologies, biogeochemical functions, and physiological responses to environmental stressors. Understanding their community composition is crucial for understanding the structure of aquatic food webs, as well as global carbon cycles. In the meantime, some other earth science questions, especially in the context of climate change. Phytoplankton contains diverse pigments in their cells that absorb light differently. They also in different sizes and shapes that can scatter light differently. So they can display different colors when observe them in bloom conditions in the field or in concentrated cultures in lab settings, as you have seen from these figures. These differences in colors are captured in reflectance spectrum as well as seen from PACE OCI imageries acquired along our coast. PACE OCI is the first hyperspectral sensor that provides global coverage of hyperspectral data daily. It is also very powerful for studying large estuaries, lakes, and coastal oceans. This beautiful spectrum extracted from PACE OCI demonstrates the contrasting spectral shifts between open ocean and coastal waters. The blue lines represent the open ocean, as you have seen here, extracted from in the middle of northern Gulf of Mexico. Within coastal zones, as you have seen here, these are different types of waters, like cyanobacteria-dominated waters, are shown with green lines right near the river mouth. And for the dark green lines from the waters adjacent to wetlands, indicating the areas with high abundance of algae and seed down. A little bit further away from fresh water, like orange lines, might represent other groups like the item, which dominate the spectrum in this area. Next slide. We understand the need for hyperspectral capabilities to study phytoplankton and their response to climatic and anthropogenic stressors along our coast. For example, in addition to warming temperature and more frequent storms, our state also investing considerable efforts in coastal restoration to reduce land loss and enhance resilience. One example is the sediment diversion project, which diverts sediment-rich and nutrient-rich waters into estuaries, but it also causes water quality issues. So we have been working closely with our state managers to use hyperspectral data to monitor coastal water qualities as PACE early adopters, especially we focus on harmful algal blooms. But initially, the challenge is how our end users, our state managers, can easily process these amazing hyperspectral data and interactively work with them. Many of us have encountered issues when dealing with these hyperspectral cubes. First, they are huge, and it's not practical to save all the hyperspectral data on local drive and for further processing. Additionally, hyperspectral data come in different formats, such as GeoTIFF, NetCDF, and HDF5. Some of them are source data, like PACE. Some of them are graded data, like IMID. Some of the data cannot be easily opened in software. Also, it might lead to software freezing due to the size of the data. Next slide. With that, we understand the need of open science. We have been following and involved with NASA OpenScapes event and fully understand the importance and the benefits of open source tools and cloud computing, especially for PACE hyperspectral analysis. In this context, we began developing HyperCoast, a Python package designed to provide tools for visualizing and analyzing hyperspectral data in coastal ecosystem studies. HyperCoast was published and released as a Python package in April this year. At 4 months old, it still has lots of room for growth, and we are currently working on the new tools to enhance its visualization and analysis capabilities. Next slide. Currently, HyperCoast supports the processing of hyperspectral data from both existing spaceborne and airborne missions such as PACE, IMID, Everest, and NEON, as well as upcoming missions like SBG and Glimmer. Most of the tools in HyperCoast are for pre-processing and visualization right now, but we are actively developing AI-based algorithm for water quality and habitat classifications. Here are some of the tools currently available in HyperCoast. You can leverage NASA's Earth Access package to interactively search and download PACE data if you have an Earth data account. You can also explore PACE data easily and interactively. You can click around and extract or export the spectra easily. You can also change band combinations and use colors to display each layer in PACE OCI hyperspectral cube. Although our primary focus is on coastal research, but these tools are not limited to coastal studies alone. You are more than welcome to try them out in other regions as well. We have published a software paper on HyperCoast in the Journal of Open Source Software. Please feel free to check it out, and here's the link. As mentioned, you can create a new environment and install HyperCoast or try it out on Google Colab. This is a short video demonstrate how you can use two functions to search and download PACE data. You can set the start date, end date, and zoom in to the area of interest and then click search. The search results will be displayed and telling you the number of images available with your search criteria. When you move the mouse, data information will be available for you to scan through, and this will also help you constrain your data search. For more details about these functions, you can visit API reference for PACE module in HyperCoast, and here's the link. Next slide, please. Next, you can use these read functions to load the PACE OCI data as an X-ray dataset. These functions can be applied to different levels in the various PACE products, such as level 2 AOP, BGC, SWOS data, as well as level 3 graded chlorophyll A data. This really streamlines the process. You only need a couple of lines of code to read in the data afterwards. You can utilize any helpful third-party Python packages for further analysis. Some functions in HyperCoast can also help you easily extract the spectral signatures at specific locations, like extract the piece, or you can visualize the loaded data using static map. But later we will explore the interactive visualization. Next slide. As mentioned, level 2 data is SWOS data, which means the data are not on a rectangular grid. You can also use a function called view pace pixel locations to visualize the irregular spacing of the pace locations for interactive displays. A graded data format is required for the interactive visualization. You can easily convert the data to a graded format using grade pace function, which is useful, very useful for the interactive visualization. Here's an example of graded level 2. Children, could you click? Yes. Here's an example of a graded level 2 BGC data. Once you read in data and convert it to graded format, you can easily display them interactively. You can change the layers such as graded chlorophyll A, POC, as well as phytoplankton carbon, showing in this demo. Next slide. As mentioned, PACE level 2 data is SWOS data, which means you need to do extra step convert it to graded data, and in order to visualization interactively. Here, we are ready to display them interactively using HyperCoast map and add pace function. In HyperCoast, you can flexibly change the band combinations and display the image composite. You can also inspect the values of single band layer by switching to one band. You just clicking here and select the color bar and for the best legend that's used for your needs. Next slide. You can also use add spectral function, and this toolbar will appear, which will help you interactively perform spectral signature extraction. And this feature enables the extraction and the export of spectral signatures. It is very helpful because while you can perceive colors with your eyes, but you cannot always directly perceive the spectrum, the reflectance trough peaks along the spectrum. This tool is useful for early detection of HAPs. You can examine the diverse spectrum from PACE OCI imageries across different water types. And later on, you will be able to export all of the pixels along their spectrum directly into a CSV file by clicking on this button, this save button. Once you click on it, a window will pop up and asking you save the file. And next slide. This is what the exported spectral data looks like. And the first and second columns indicate the band number and the wavelengths respectively. And the first row provides location information, while the subsequent values represent the reflectance at each wavelength. Next slide, please. For the spectra that we have observed from PACE imageries compared to in situ spectra, for example, here I use cyanobacteria bloom water as an example. You can see high similarity between PACE observed and in situ spectrum. you can identify specific features of cyanobacteria bloom waters, such as the chlorophyll A absorptions in blue and the red region, and the phycocyanin absorption at 620 and 650, the fluorescence at 650, also the near-infrared scattering around 700 nanometer. In the past, with multispectral satellites, the 650 nanometer band was missing. However, the ratio of 620 to 650, as well as 670 to 700, can be very useful for detecting cyanobacteria bloom waters. This data was acquired I think on July 31st this year. We only have field data to show to validate the map in the Northern Gulf of Mexico. But if you zoom in, you saw that the cyanobacteria affected waters is really just in Louisiana as well as in Florida, this Lake Okeechobee. But this ecologically makes sense as Louisiana is more affected by fresh water, where cyanobacteria is more prevalent in our estuaries. Next slide. In HyperCoast, you can also use some common spectral analysis methods like spectral angle mapper. Spectral angle mapper determines the spectral similarity between two spectrum by computing the angle between them. You can further classify cyanobacteria affected water into different risk levels as shown here. But this is just an example. We use this library acquired from cyanobacteria dominated waters at different levels of chlorophyll A concentrations. Based on this simple algorithm spectral angle mapper in HyperCoast, we can further classify these cyanobacteria affected water into different classes. But one note is that the library is very important because the spectral angle mapper's accuracy is highly sensitive to the choice of reference spectrum. Later, we will also talk about the importance of establishing good spectral library. Next slide. Lastly, I want to showcase a tool relevant to field data in HyperCoast. As we all know that field observations are very important for satellite algorithm development as well as validation. So we include tools that can easily compare field observations with PACE OCI data, simplifying the process of matching satellite imagery and the field observations. You can use add KML or add points to easily add the example, for example, add the field data, for example, the cruise track or the observation points. As long as you have a KML file or CSV file ready with coordinates. In this short demo, we are showing our sampling size from this summer when we participated in NOAA hypoxia cruise. We did shelf sampling in the Northern Gulf of Mexico. If you click on the sampling sites overlaid on top of a PACE OCI imagery, the corresponding measurements such as dissolved oxygen, salinity, and temperature will be displayed at each location. You can easily show, you can also show the radiometric measurements, the spectrum, which I will show later. Please note that the track, can you go back? Oh, it's fine. We can go to next slide. All right. In this demo, as I mentioned in my last slide, if you have CSV file ready with your radiometric measurement, for example, the remote sensing reflectance spectrum, you can display your measured spectrum, field measured spectrum here and compare it with PACE spectra. We are still in processing of analyzing our field measurements. So the spectra I'm showing here just the example of remote sensing reflectance spectrum derived from PACE, but you can replace this spectrum with your field observations, so you can compare your in situ observations with PACE extracted spectrum using this tool called Add Field Data. Next slide, please. Well, with that, in this slide, I will show you where you can find HyperCoast repository, which include example notebooks for different hyperspectral missions. And the link below is specifically for PACE notebook. With that, I will hand it over to Qiu Sheng, and he will go through the notebook as a lab demo.
Okay, let me see here. Stop sharing. Can you see my screen? Yeah, so I'm just quickly go through the where you can get the Jupyter notebook. So if you type HyperCoast on your the URL, and then you should get to the HyperCoast website. And this is the website. You can also click up right here to go to the GitHub repository if you want to look at the source code. So everything is open source. We also welcome your contribution. So specifically for PACE, if you on the left side here, if you click examples, there are a lot of examples dealing with all kinds of hyperspectral data. So we have some for PACE, emit, and also other types of hyperspectral sensors. And for today's presentation, we put together a PACE notebook example here, so you can basically get an overview of what kind of functionality that we have for PACE data. So it allows you to source data, download data, and then visualize the data. If you want to try it out, all you need to do is here, you can open in a Google Colab, and then just log into your Google account. Uncomment this one, just install the packages, and then you should be able to just go through. So everything is reproducible. You can also click on the left side here, you can go through the table content. And because we don't have enough time, I just want to quickly show you the examples here. Oops. I have already opened this one in my local computer, so you can also set it up on a local computer. And after that, you can see you can source the data. So this built on top of the Earth access package, but makes it easy for you to visualize because you can just one line of code, you can search, and then you can pass in the location, the bounding box, the time period. And so you can visualize the footprint easily. So you can see how many images are available in the area. Then you can just one line of code to download the data to your computer. And after that, you can just add that for visualization. And also you can just call the function. For example, you can just create a map and then just search page. It will pop up an interface like this. So I can just show in here. And once you create a map, and then you can just zoom to any location. Oops. So for example, zoom to any location you like, and you can either draw a rectangle, or you can just go into search the data in the map view. And then from here, I can just search whatever time and date you like. So for example, April 1st, and you can specify the end date. And after that, you can just do a quick search. You should be able to return all the results very quickly, so you can see all the bounding boxes. You can also see from those down list. Right now, you cannot visualize directly yet, but it shows you like what data available for the area. And not just for the PACE AOP, you can also basically source any data available in the NASA Earth data catalog through the Earth access package. So there are a lot of data sets available here, and then you can basically it's not just for PACE. You can do it for all the data. Once you download the data, then you can just load the data. For example, you can look at download a sample data set, and you can use the function to see the non-greedy. Basically, this is just the pixel locations like this, and just one line of code to read the data into an X-ray data set. And then you can there are two ways you can visualize data. One is just doing the static visualization. So it's just going to print out something like this using map, plotted, and also CardioPy. And you can also overlay some like state boundaries, something like that on top of the map. So this just provide you a quick visualization. You can extract the spectral signature. So under the tool, we do a lot of like pre-processing. So you don't need to write many lines of code. Most of the things you can do just one to two lines of code. You can also extract all the spectral signatures within your area of interest, and then you can combine them all together on the same map. So the most, interesting thing in in HyperCoast, it allows you to do visualization interactively. So if you just create a map and then specify the data set, whatever data set you want. So for example, after I read the data set, let me go back to here. So most of this functionality, all you need is just one line of code to read the data set. So for example, this is you just point to the file path. For example, this is the PACE data set, AOP version 2 data that I downloaded, and then you can just one line of code to read the data as an X-ray data set, and then just another line of code to visualize them. So I'm gonna go back to this code block in here, and so you're going to create a map and then specify the spectral band you want to visualize, and then just one line of code add paste to add it to the map. So this one under the hood is reading the data and then also doing the greeted, because paste label to the ALP data is not greeted data. So it's doing the data processing and then add the color map, and you can take a look. This is what it looks like. And you can click your mouse on the map. It's going to extract the spectral signature easily. So allows you to do visualization. If you just need, so this one, you can stack multiple spectral signatures together, for example, here. It makes it really easy to visualize. If you want just one single one, you can also do it like this. So you can stack them all together, and you can also change the visualization. So if you just want, for example, one spectral band, and you can change to whatever spectral bands that you like, and then select. And you can also change, for example, the color mapping here. So in this way, you can like explore data, find out the which spectral band is most useful for your user case, and then you just hit one apply. So under the hood, it's going to read the data and then read the data and then just plot it on the map. So you can try them out. This is sometimes might take a couple seconds to display the data because it's reprocessing the data. So and then but it's going to allow you to visualize them interactively. So you can see here right now I'm using a different spectral band, and I'm band 93, and then you can see it's being loaded after a couple seconds, and really easy to do. So you don't need to write many lines of code in order to do that. And same thing here. You can click on the map. This might be a bug. It's supposed to pull up the spectral signature and something just like this one. So you can do it one spectral band or multi-spectral band, and you can also basically read the data. So let me try this one more time here, just in case. So if you click on the map, if you want to extract some spectral signature, so for example, you have some a few sample data set, and then after you, for example, click some of these, right? And if you want to save this one so that you can do some further data processing, you can easily just export them as a pandas data frame. So it's kind of presented as a table format. And so you have all the points in here. You can also convert them to a geodata frame if you want to plot them on some GIS software. So you can have basically reorganize the data, and then after that you can save this one as a CSV. So basically allow you to visualize the data interactively, and then also change different band combination, mostly just with carbonized code. So it really simplifies the kind of the data processing workflow. And besides the ALP data, you can also visualize the BGC data. So it's very much similar. So you read the data set by just using a different function, and after that you can look into the data set. You can also do all the visualization. My light's off. And so you can either static visualization, or you can do interactive visualization. For example, like this one in here. So you can basically, depends on what kind of data available. So you can use that to visualize all the data layer together. You can also change the base map to whatever base map you like. And these are all interactive. So you can quickly see what the data looks like. And then you can start thinking about what kind of things you want to do for them. So this is so much better than just print out a static map, because it's hard to see the detail. And with that on the interactive map, then you can do more in detail, in-depth inspection, and also support level 3 CRO-V8 data. So this one allows you also to process the data. For example, you can download this one. We're downloading the daily data. It's aggregated from, I think, 8 days. So we have the daily CRO-V data, and you can just read all the data all at once, one line of code, and then it's going to construct an X-ray data set, and that allows you to look into individual. For example, just looking at a single day, looks like this, or you can just combine it all together. So this one, I think, has how many days? 17 days, for example. And then you can just do a simple using X-ray to do aggregation, and then you're going to end up with a map like this. So this is the average. But you can also visualize them on the interactive map. So it's going to look like something like this in here. And again, it's better than just print out on a static map, because you can see them interactively and zoom in and zoom out, and you can turn the layer on and off. So pretty much it's just one line of code, add raster. So it can be a single image or it can be a average image that you have already do all the aggregation. So this one is the 17-day average of the page data. And again, you can see something like this interactively. And also, this is like Bing-Qing mentioned about the inside view data. So you can see if you have some field data, you can do data processing, and then you can put them all together. So this one shows you in here. For example, you can have all the points, and you can click on them to see the sampling location. And so right now, it's kind of separate. So you can overlay multiple data layers together. So in the future, we'll be able to, when you click on a point, we will be able to plot both the in situ measurement and also the satellite measurement, for example, the page spectral signature together. For now, it's just individually. So for example, you can zoom in. So if you click your mouse on the map, right? Oops. You'll be able to get all the spectral signature of the pixel. So in the future, we'll be overlaying the in situ data altogether. So this will be going to the last example here. Yeah, this one. So for example, you click on the point. So this one is going to show you, assume this is the in situ data set. But you can also click on there to get some the spectral signature of the satellite data. So this is about how you can use HyperCoast to easily download the data, source the data, visualize the data, extract some data. And so lastly, there is also another notebook about doing some analysis. You can also try it out. We don't have time, but you can see some of the things we can do. So in the future, it'll be much easier. Right now, it's still lots of lines of code in order to do some of those analysis. So we plan to add more like deep learning related algorithms to this. So user can just a couple lines of code, then you can do some image classification or segmentation, or even doing some multi-class classification easily in the future. So yeah, that's what I want to show you. I'm happy to take any questions.
Excellent. Thank you very much. This is fantastic. This is a very powerful tool, and these are some fantastic resources here. Looking through the questions, we have a couple minutes here for questions. If anybody has any, you can put them in the chat. We had one that was answered in the chat. Let's see. I think I actually lost track of it. Here, let's answer this one here. Is the HyperCoast pace data atmospherically corrected?
We just use the original data. We haven't really done anything. So it's there's we have an example using the Ecolite. It's also on the HyperCoast website. You can try it out, but we haven't really done any additional data processing. So let me send the links in here. That we can probably add another examples in the future to do some atmospheric correction.
You're using the data straight from
exactly
NASA,
from
right?
what we did is only grid data into rectangular data, so we can plot on the interactive map. But we haven't done any additional atmospheric correction on top of that.
Great. Let's see, another question. Did you use elements of ArcGIS to make these interactive maps or just X-Array?
No, just X-Array and then a leaf map. So it's open source. It doesn't rely on any commercial packages. You can look into the source code. So all the functions source code available on GitHub. So it's just using leaf map built on top of IPyLeaflet. So it's a Python package. You can actually also do 3D. We didn't have time to show it, but you can also overlay the data on a 3D space.
Great. Thank you. And then we have, can you say more about support for HARP2, SPEX1 data in HyperCoast?
Right now, that's what we have right now is to support those we use and also some of the common data set. But if you have any specific things you want to see in HyperCoast, feel free to reach out to us, or you can submit a feature request on the GitHub repository. We're happy to add more support for all kind of data. Because HyperCoast have so many data products, we're trying to add more and more. Right now, the mostly AOP, BGC data and level 1 to level 3. You can check some of those notebooks on the website. If there's something that's missing or you want to add, suggest, let us know. We're happy to add support for that.
All right. Excellent. So does we have time for one or two more questions? Can be on either presentation. Yeah. Ming says, thank you for your answer. It would be interesting to do cross comparisons using HyperCoast. So he responded. I guess that with that, let's see. Oh, there's one more question here. Let's see, how soon will CDOM, so CDOM absorption, and DOC, dissolved organic carbon data be available? So is that enough of the question to make sense?
Thank you. Yes, our HyperCoast are trying to support different water quality algorithm as well. So right now it's only for visualization, but later on, we will incorporate some AI-based algorithm for water quality parameters. Even though we focus on phytoplankton like chlorophyll A and like phytoplankton absorption coefficients, we're also interested in including more water quality parameters like sediment and carbon.
Great. Thank you very much for that answer. We have 1 minute left, and I think that with that, I don't see any more questions. So I want to very much thank you guys for your presentations today. Bing-Ching, this is wonderful work, and Chu-Shen, both of you, this HyperCoast tool is fantastic. We thank you guys both very much for being here, and thank you, Jeremy, for our updates. We will catch you all at the next meeting, or hopefully at our upcoming workshop on December 8th in Washington, D.C., or at our RSET course coming up next month. With that, I will say goodbye and thank you.
Thank you, everyone. Take care.
Bye.
Bye-bye.
Thank you. Bye.